let's kick it off because this topic is too exciting to wait any longer. So let's all give Jens a hand as he presents benchmarking SNARKs.
Cool. Thank you very much. So today I'll talk about the performance characteristic of SNARKs. This is joint work that we did in the past around like 3, 4, 5 months, with a bunch of collaborators. Okay, so let me actually motivate a bit why we care about evaluating the performance of SNARKs in a more systematic way. I kind of looked through the talks of ZK Summit 7, 8, and 9, and exactly the conversation that just came up. Basically, it could have been a problem earlier, as there were like a bunch of like 29 out of like 61 talks I found had like some relevance with regard to performance, but were always like considered in an isolated environment. So it's quite difficult to track the performance improvements and also like practical implementations, even for experts, which I guess like a lot of you are. I guess no one could really recollect what these 29 talks actually like, how they compare to like other implementations, right? Okay, cool. So let me quickly state what this talk is going to be about. So first we're going to talk about clarifying what do we actually want to measure in SNARKs. We're going to introduce the work that we actually did on a benchmarking framework for SNARKs and zero-knowledge proofs in general. Interpret some preliminary results and then outline how we like as a community actually improve performance benchmarking. Okay, at the same time, I also want to delineate what this talk is not. So we're kind of a team of academic researchers, so this talk is not going to be biased. We're also not going to talk about a direct comparison of SNARKs and pairing-based SNARKs, which has gathered a lot of attention recently, I think. And also, some of the results presented here are not timeless, right? So most of the benchmarks always depend on like how the circuit is implemented and on different optimizations, and these can change results significantly also in the future. Okay, and we're also not trying to decide which proof system is the best. Okay, so probably a lot of people already know this, so I'm quickly going to skip over this. The important part in this case about SNARKs is what do we actually want to benchmark from a theoretical perspective. Most implementations always rely on pre-processing SNARKs. So in a pre-processing SNARK, you have a split setup procedure where one part is randomized, right? Like, for example, a trusted setup or like a trustless setup where you generate a common reference string. And then you also have a deterministic setup procedure where an algorithm that is commonly referred to as the indexer takes the common reference string and the circuit description and outputs the prover key and the verifier key, which can then be used by the proof and the verifier algorithm. From a practical perspective, this is mostly how most of the implementations of SNARKs look like in either like CIRCOM, GNARC, ArcWorks, or whatever. This kind of shows what we want to benchmark in practice, right? So you always have a front end. The front end allows you to encode the circuits and provides kind of like an intermediate representation, which can either be, for example, R1CS, AIR, or whatever. And then you also have the back end, which is more interesting because this is like where it actually becomes fairly performance intensive, where you have the setup algorithm, which in this case is the indexer that I mentioned before, that generates the prover key and verifier key. You have the prover, which is probably the most compute intensive part, and then the verifier, which can be, depending on the actual proof system, either constant time or, yeah. And the important metrics, I guess, that we want to measure here are the execution time for the setup, the prover, and the verifier algorithm, as well as the memory consumption for these algorithms, as well as the proof size of the actual proof, right? Which might differ between like different proof systems and implementations. Okay. At the same time, is this actually enough? So if we want to measure the performance of a SNARK, does this suffice for everybody that is trying to develop an application with SNARKs, right? So usually when you want to develop an application with a SNARK, you have some kind of idea, you have some kind of system design, and then you have to figure out whether you need a custom proof system or not, right? And if you need a custom proof system, for example, that happens with Zcash for Halo 2, with Plonky 2, FLONK, that you kind of need custom optimizations for whatever you want to do. You need to figure out which arithmetic library you actually want to use to implement that proof system. And on the other side, if you don't need that, if you don't just want to build an application, you want to kind of like figure out which domain-specific language or library is like optimal for exactly that. So given all of these like kind of considerations that you have from both a theoretical, practical, as well as like an application side, what would be the requirements for a framework that kind of allows the benchmarking of SNARKs, right? So on the one hand, it should be holistic. So we want finite fields operations, elliptic curve operations, as well as end-to-end circuit executions. We want some kind of modularity. So it should be easy to both add like a new library to the proof system, but it should also be easy for an integrated library to just add a new circuit, such that you can include some kind of like custom developed circuits with new optimizations and easily just rerun whatever you had, right? And at the same time, it should also be reproducible and also pragmatic, right? So it should kind of like resemble a practical setting. Right, and on the quantitative side, as I mentioned, execution time, memory consumption, proof size, and statistical soundness are kind of like of relevance. Okay, so this is kind of what we came up with in the recent month. So we have a benchmarking framework for SNARKs, which is both an arithmetic backend as well as a circuit backend that kind of holistically covers the whole SNARK stack. So on the arithmetic side, you have libraries like, for example, ArcWorks or GNARC Crypto, which SNARK development tools then rely on, where we measure the execution time of, for example, field addition in the scalar field, addition and multiplication and in G1 and G2, as well as multiscalar multiplications and pairings. On the circuit backend, on the other side, you can have like some kind of like configuration file and some specification of inputs that you then input into different integrations of different SNARK frameworks. And then we have some standardized logs. We try to use state-of-the-art performance measurement frameworks, like, for example, Criterion, to measure the execution time. And we separate measurement of execution time and memory consumption by basically compiling independent binaries, for example, for proving, verifying, and the individual setup procedure. And then we also have two front ends. One is focused more on the arithmetic side, as well as one that is focused more on displaying, dynamically displaying the circuit benchmarks. Okay, so if you remember the requirements, one of them was also like the ease of extension. So for example, if you have like a library that you want to integrate, let's say GNARC, takes around 80 lines of code. If you want to add a circuit to exactly that, takes around like 30 lines of code. And for domain-specific languages, like for example Circom, it was around 250 lines of code to integrate the whole thing. And then like it's pretty easy to just add a new circuit and run it again. Right, so this is the current scope that we integrated and that we kind of like ran some benchmarks on that are also open source, by the way. We have a bunch of curves, the pasta curves that are used in Zcash, GNARC Crypto, which has a variety of different curves, ArcWorks, Halo 2 curves, which is fairly new and I believe is being developed and like optimized at the moment. But we also have like more traditional integrations such as Curve 25519 Dalek, which is, I believe, used by, I think, 80,000 repositories or something, just as like a baseline comparison. And on the circuit side, we integrated Bellman, the Halo 2 from PSE with the KCG polynomial commitment, GNARC, Circom, and Starkey. And we focused on the curves PN254 and BLS 12381. For at least like running the initial benchmarks. You could run it over like any arbitrary curve in GNARC, for example, but we focused on these due to relevance in Ethereum. Right, the current circuits that we integrated across those like 5 frameworks are simple exponentiation circuits, so just to simulate like a set of dummy constraints up to, I think, 2 to the power of 24, which is around like 16 million constraints. as well as SHA-256, which is more of a realistic payload. And the reason for that is pretty simple. It was already like implemented in most of the frameworks, actually not in all. And we could just use it without like having an unoptimized custom implementation that we do ourselves, right? So we run all of this on different machines in AWS. Some of them are smaller, and others of them are more like server-sized with 128 gigabits of RAM, and 32 CPU cores with different CPU architectures. So we have x86 and ARM. And we also have on the bottom 2 different machines, where one is more optimized for memory consumption, and the other one is more optimized for CPU computation. Right. So to show you some of the initial results, here you can see the results for the arithmetic backend for multiscalar multiplication in group G1, multiscalar multiplication in group G2, as well as pairings for both curves BN254 and BLS12381. There's a couple of things that you can see here. For example, GNARC crypto so far has the fastest implementation due to several optimizations. For example, all the way in the back, you can see that for larger MSM instances, both actually BLS-TRS, this, and GNARC crypto use batch affine addition. And for smaller MSM instances, you can also see that FF JavaScript and BLS-TRS don't enable multi-threading, which is why they have like a little bit lower performance for smaller MSMs. Then when it comes to SHA-256, this is quite optimization dependent. In general, what you can see is that the memory consumption for frameworks that are built in Rust is quite a lot lower. At least that's what we experienced. But as I'm speaking, there has been like new optimizations, for example, in GNARC with 40% less constraints, which would render it like a much less computationally intensive, right? Right. Works. Same goes for the exponentiation circuits. Here, just as a reference for the proof size, you can see that the STARKey proof size is quite a lot higher, around like, I think it was like 600 times, at least for 8.4 million constraints or rows. And for memory consumption, we observed kind of like the same thing. What we have to note here is that the STARKey circuit is not optimized. So you might see that like STARKey in this case is a lot slower, which is like probably a lot of, like not that expected as in comparison to GNARC or Rapid SNARK. And the reason for that is pretty simple. In this circuit, we have 3 columns. And STARKey would be optimized more for wider traces. So if we had like 10 columns and less rows, you would see like a significant increase or like decrease in execution time for this. Yeah. Okay. When we were also interested in looking basically in these 2 machines that are like where one is like more memory optimized and one is more compute optimized, kind of to figure out whether one or the other kind of like influence the performance of a specific like proof system. And what you can see here is, for example, that I think you can't really read it, but that like one row up there that is like fairly black, that is a Rapid SNARK in BN254 with groth 16. And here kind of the darker color means that the execution on a RAM optimized machine outperforms the CPU optimized machine. And the number that is stated in there is a 1.4. So in that case, it outperforms the CPU-optimized machine by 40%, only by running it on a different machine. And you can observe similar things for GNARC, where it's like a little bit like inverse, right? And that is like across both circuits. So on the top, you can see the SHA-256 circuit, and on the bottom, the exponential circuit. Okay. So one thing that we asked ourselves now that we have like this holistic framework of arithmetic benchmarks as well as circuit benchmarks, can we estimate the circuit runtime, right? So given like, for example, you have Plonk. This is like, for example, on the left, the table that is Plonk with GNARC. over BN254 and BLS12381. Can we estimate from the number of multiscalar multiplications, FFTs, and so on, can we estimate the actual runtime? The answer is actually yes. This is not really optimized, so we ended up with like around 6 to 30% of being off. It gives you like a notion of in which kind of like range the execution time is, but it's not super specific so far. And also it's like not a generic methodology because different implementations use different optimizations. For example, in Graph 16, you have in the verification step 3 pairings. If you do it like in a simple fashion, you would have to do 3 Miller loops and 3 final exponentiations. Whereas like in practice, it's very common to use optimizations where you only do like 3 Miller loops and then one final exponentiation, which you have to consider in the estimation process. Right, and our benchmarking data is open source, so if anybody feels like improving on that or including something like that in like a compiler or an IDE, we would be happy to guide you through or help with that. Okay, some of the recommendations. I think one of the things that we experienced is that it's fairly hard to compare performance if there's no kind of like standardized payloads that you can use. So it's fairly hard, like if there's like custom implementations of SHA-256, if you like realize there's no star key SHA-256 in these, that was like a very conscious decision because we looked at the implementation and it was fairly, there were no tests for correctness, let's say like that. Really having standardized payloads by the projects that actually also develop these libraries and kind of acknowledge like optimal usage of a framework would make like really like leveled comparison much more easy, and also an agreement on hardware specifications for evaluation would also make a lot of sense. Right. Yeah. Good. So what would be further work that we can do in performance benchmarking? So in general, I think there's still a lot of work to be done in our framework to kind of like make it more holistic in a sense of optimizations. We currently don't really include any comparison of lookups or any comparison of recursion. And we also don't really care for the optimality of arithmetizations. And so these are some of the things that we really want to look into, and also the whole estimation of runtime that I've like gave a glimpse into can be done independently from like whatever is done in the framework. Our data is open source, and if you want to look for more complex circuits that include lookups and estimate the runtime for that, I think there's a lot of room for optimization on this one. Exactly. And yeah, we only have like 5 different frameworks integrated. I think there's a lot of different ones that we can still include. Okay, if you want to take a look at what we've done, we have the 2 front ends, which is zcalc and zkbench.org. Second one is not yet updated with the results that I've shown in here. That's why I had on the previous slide, we need someone who does like front-end development. If you want to look at the data, there's the GitHub link. And thank you so much. And also there's going to be a preprint of a paper very soon that discusses the results in more detail. Looking forward to that. Thank you.
Amazing talk, very important work. Any questions?
So if we want to add a library or a framework for benchmarking, we only need to create a PR on bench data?
Not on bench data. It's called like github.com/zkcollective/zk-harness. There's a bunch of we have some documentation. Currently the branch is v0.1.0. We plan to merge that once we updated the front end. But yeah, essentially the only thing that you have to do is follow whatever description we have in the README, and then create a PR to basically integrate that, and then we can run it with some of the funds that we have for benchmarking.
How do you use Criterion, which is Rust specific, with JavaScript or Go?
Yeah, we use a different library for that. We can't use Criterion with Go or JavaScript. Yeah.
So if we use C, C++, other languages, you can just call from Rust and use Criterion for this, right?
No, for that not. But we open a PR and we can discuss, like, we haven't done any like C++ C integration yet, so we don't have any like specific benchmarking framework that we use for that yet. But I'm sure there is something that we can use that is C specific. So it's not like Criterion was only an example for Rust.
Thanks.
We got a question in the back. You mind getting that one? Thank you.
Do you know if there's any like MSM benchmarks where you limit the scalar weight? So in last one, Joel's, they claim that, basically when you do MSMs, when you do it on random scalars, it's always going to be, more expensive. And most benchmarks are doing it on random scalars, right? While in a lot of systems, you actually have a lot of, non-random scalars that generate from the trace. Do you know of benchmarks that's, particular to that?
Can you quickly repeat the question?
Yeah, so in some, basically when you limit the MSM to scalars that have low weights, for example, when you have a 256-bit field, but you actually have scalars that only have 32 bits, in length,
yeah,
then it's faster, right? Do you know of benchmarks that targets that particular use case?
No, so far I don't know of any benchmarks. We didn't integrate that, like, or didn't consider small fields so far. Yeah.
Hi, ZK here. So, like, for the arithmetic part, we don't do that, but it's also a choice because you just want to write whatever you write in paper, you have benchmarks for it. It would be a nice addition, but also there is a restricted number of operations that we can do.
And I was going to say, ZPrize, when we did the MSM acceleration last year, it was randomly weighted scalars, but this year we're doing more, the focus is more on end-to-end, like applications like ECDSA verification, like a Merkle tree or a Merkle proof in Poseidon. So potentially in those cases, you might have more structure. And so hopefully the results that will come out of this year's ZPrize, might be indicative of what kind of performance improvements you could see, at least on specialized hardware, for those types of problems, possibly. Sorry, we all helped in answering your question. Cool.
Is there a plan to add GPU for your harness?
Yeah, we could definitely do that, but we just didn't have the time to do it yet. So yeah, it's kind of difficult to set priorities, like, because there's like so much stuff. So we're really hoping like that, like, some people will contribute and like make this more holistic, so we can have like a really like standardized performance comparison, right?
Also, just commenting on that from the ZPrize perspective, I think optimizing GPU, like having it be optimized for GPUs is kind of different than, just writing it generally for a CPU-based architecture, I think. Yeah. So if you look at ZPrize, if you go to the ZPrize GitHub, so ZPrize 2022, you'll see some, at least MSM, GPU-optimized MSM implementations. And there's some really great videos, actually, at Stanford, their equivalent of RDI, Center for Blockchain Research, where people have kind of done some talks about specifically how to optimize for that. And the speed up is pretty dramatic.
So the idea is so that people can just run the harness maybe on their own machine or their own Amazon or whatever, so that they can compare. Because since ZPrize 2022, things evolved. We had this iRead plus ZK10 fused solutions, and we don't have the benchmark data. While if we had this, we could rerun and make sure, and then hardware changes. So we'll likely have soon new NVIDIA GPUs. Maybe people will develop on Apple Metal. So.
Yeah, I mean, one of the things that we also wanted to do is more like have like more of a CI/CD architecture, where essentially like to make it easier for like library maintainers to like just like submit a pull request like with an optimized circuit, and then like I don't know, you accept the pull request and like it runs everything like in the background. But for that, we also need some more funding to actually like do that stuff, right? Yeah.
Yeah, it would be amazing to have a universal harness. And I know for a fact, I might talk to Niall from Yared about this. You know, for this year, we were actually including like the 4th generation NVIDIA GPUs, and I think the implementation potentially would look very different given like the different memory architecture in those GPUs. So, here, oh, here.
Sorry. For funding, maybe, so I don't know if you looked at the protocol guild on Ethereum. It's a way to fund infrastructure work. And that could be one thing, because many companies like Lido and others are contributing to it. Millions now and they just give 0.1% of their revenue to this, and this is enough, I think, to get this, and it's worthwhile for everyone.
Yeah, definitely. Yeah, we were actually supported by a grant from the Ethereum Foundation for this initial work. But yeah, I agree, definitely. I'll look into it. Yeah.
So guys, I think that's it. I'm the only thing standing between you and lunch, unless we have any final questions. Okay. Thank you, everyone, very much. We'll re-meet back here at 2 o'clock, so we have an hour lunch break. Thank you, everyone, for your attention. Let's give
Thank you.
Jens another hand. Thank you.